Welcome to Advanced Quantum Chemistry and my 8th lecture on Hartree-Fock theory. And in this lecture I want to show you how one gets from the non-canonical Hartree-Fock equations, which we had derived in the last lecture, and which are not an eigenvalue equation, to the standard Hartree-Fock equations as we have seen them in the first lecture, which are an eigenvalue equations. These standard are called the canonical Hartree-Fock equations. And we're going to do that by making a unitary transformation of our orbitals. So what is that? Now let's take our spin orbitals, which we have assumed obtained by solving the non-canonical Hartree-Fock equations, and make some linear combination of all these orbitals in order to make new spin orbitals psi I tilde. And all the linear combination coefficients we put into a matrix U, and it's called U because we require this matrix to be a unitary matrix, so that the whole transformation is a unitary transformation. It's called a bit of linear algebra. A unitary matrix has the property that the inverse of this matrix is actually the same as the Hermitian conjugate of the matrix. And Hermitian conjugate means that one takes the transpose matrix and then the complex conjugate of all of the elements. And the very nice property of a unitary transformation is that it preserves the orthonormality. So if I apply unitary transformation to a set of vectors, or here spin orbitals, then which are orthonormal, then the new set also will be orthonormal. Now the question is, what happens to our Slater determinant if we make these linear combinations of our original spin orbitals to form new spin orbitals? Well, making the unitary transformation is, as I said, just making linear combinations. And now remember that the Slater determinant is built up in the way that you either have the same spin orbital in one column, so each column corresponds to one spin orbital, or you can do it with the rows. But let's say we have it with the columns. So making a linear combination of the spin orbitals means that we actually add multiples of one column in the Slater determinant to another column. And from your mathematics course, you should sort of might recall that if one adds the multiple of one column or a row to another column in the Slater determinant, then the value of the Slater determinant does not change. Now our wave function, our Hartree-Fock wave function, is precisely the value of the Slater determinant, and that means that making unitary transformations of the orbitals within a Slater determinant actually does not change the wave function. Okay, so far so good. The Hartree-Fock wave function does not change by making this unitary transform. How we calculate it, or how we formed this tilde orbitals, meaning we have to insert this one for both U adjoint, Hermitian conjugate, is the same as U inverse. What about the Fock operator? So what about the Hartree-Fock equation? So the Fock operator. Now let's look at the Coulomb operator, and let's look at the some of the Coulomb operators in this transformed basis, so tilde. So now we have the Coulomb operator. We have now psi tilde here and psi tilde there. To see whether this operator is actually the same as the original operator, we now have to insert this unitary transformation. So we have to insert the integrals, both of the spin orbitals. So let's start first with psi tilde j here. So this is going to be a sum now, and let's say it's a sum over L, psi L, and this coefficient ULJ then. And similar for psi j complex conjugate here. The only difference is that now we have, of course, we have to sum now over another different index and L, so we sum over K, and we get psi K complex conjugate, because we start with complex conjugate, and then of course we also have to take the complex conjugate of our coefficients in the linear combination, meanings of the elements of our unitary matrix. And since these coefficients, they are just numbers, I could take them, or can take them out of the integral, which I already have done here. And then I've rearranged also the summation because I mean, you sort of always can do that. So let's look what the term here in the parentheses is that I've written here once again. So this is the sum over j of the product of two elements of this unitary matrix. The first thing is I sort of change the order, and I always come in, these are numbers, I can do that. So I have put this one in front, so I have ulj, and then this element here, ukj complex conjugate, this is just an element, this is the jk element of, let's write that, this is the jk element of the adjoint matrix. So it's a jk element of the k element of the adjoint matrix, which means that I can, and this is summation here, it's just the summation which you have when you do matrix product. So this is actually an element, the LK element of the product of the U matrix and the U adjoint matrix. And if you remember now that, then of course I have U here and the inverse of U, and that of course gives a Unix matrix. So this product is just a Canonical delta LK. And that means that the summation over K and L here collapses to summation over K. And we arrive at this one, and that is just the normal expression for the Coulomb operator in our original, with our original spin orbitals. Which means the Coulomb operator does not change by unitary transformation of the spin orbitals. And the same also applies to the exchange term. So the Fock operator does not change on making this unitary transformation of the orbitals. Now finally, let's look at the orbital, the Lagrangian multipliers here. Let's look, the Lagrangian multipliers are the a matrix element of the Fock operator, and here in the tilde basis. So we're here with the tilde spin orbitals, and again we insert the linear combination, how they are formed from the original spin orbitals, and I move them again out of the integral, and I can write k and l, and this is my Lagrangian multiplier in the original basis, epsilon kl, and so I get this expression here. And that's again a matrix multiplication. Actually, it's matrix two matrix multiplication. So this is an element of the trivial product of u dagger, epsilon, and u. Now, and which means this is the unitary transformation of a matrix. Now, the Lagrangian multipliers, as we said in the last lecture, the matrix of the Lagrangian multipliers is a Hermitian matrix. And from linear algebra, you might know that any Hermitian matrix can be diagonalized by unitary transformation. So it's we can sort of choose, which means we can choose this U to be such a unitary transformation that it diagonalizes our matrix of Lagrangian multipliers. So this E tilde matrix, epsilon ij, is then actually a diagonal. And that means we can make a unitary transformation of our spin orbitals in such a way that the matrix of the Lagrangian multipliers becomes diagonal. And in this way, then we arrive at the HartreeFock equations in the canonical form, in the standard form, where it is an eigenvalue problem, and the eigenvalues are our orbital energies. That means actually that these matrix of Lagrangian multipliers, which we introduced as Lagrangian multipliers, suddenly becomes a completely different physical meaning, because when we diagonalized the matrix of Lagrangian multipliers with this unitary transformation, then we suddenly the eigenval elements of the diagonal matrix turns out to be the orbital energies, the eigenvalues to the Fock operator and the orbital energies. So summing up, we have two forms of the HartreeFock equation. We have this canonical HartreeFock equation, which is an eigenvalue problem, where the spin orbitals are eigenfunctions to the Fock operator, And the eigenvalue to this eigenfunction is this epsilon e, is what we call an orbital energy. But we can also transform our spin orbitals to another set of spin orbitals. And as I showed you before, the Slater determinant, and therefore our HartreeFock wave function does not change when we do that. And also the HartreeFock energy, if the HartreeFock wave function does not change, the HartreeFock energy, of course, also does not change. So we can make a unitary transformation of our spin orbitals, which we have in the HartreeFock determinant, to another set of spin orbitals, which will give the same HartreeFock energy, the same HartreeFock wave function, but which might no longer lead to a diagonal matrix of Lagrange multipliers. And there are actually these two sets of spin orbitals exist, because when we solve the HartreeFock equation in this canonical form, the spin orbitals we get there are typically delocalized over the whole molecule, which means you cannot identify one particular single, for example, in methane. You will see that you cannot identify individual orbitals corresponding to one carbon-hydrogen bond. These would be localized orbitals. But we can make a unitary transformation of our delocalized orbitals, which we obtain, delocalized canonical orbitals, which we obtain from this eigenvalue problem, to a set of localized orbitals. So they look really like carbon-hydrogen single bonds. But by doing that, we lose the fact that the matrix of the Lagrange multipliers is diagonal. We come to the non-diagonal, non-canonical form of the HartreeFock equations. And the consequence of that is that these localized orbitals do not have orbital energies. So if you want to have orbital energies corresponding to your orbitals, you have to go for these canonical orbitals, which are normally delocalized over the whole molecule. But if you want to have localized bond orbitals, you can also get that. You still get the same HartreeFock energy, but there are no orbital energies anymore.